Right, welcome to today's revision session. It's going to be on graphs and we're going to be looking at quadratics to start off with. To do this, you're going to need to be able to do factorising, and you're also going to be able to complete the square. So if you're rusty on that, you may find you need to go back and look at that lesson from earlier in the series. So first of all, we're going to find the roots of this quadratic function, and I'm going to give you 60 seconds to have a go at that. Right, so here we go. Now, to find the roots of a quadratic function, what you are looking for is you're looking to see where the function crosses the x-axis here. And where it crosses the x-axis is where the y value equals 0, and the y value is the f of x. So this must equal 0. So we start off with making that equal 0. And then we're going to simplify by, we can see this is all divisible by 3. So divide by 3, divide by 3, divide this by 3. And then what I'm going to do is change the signs, because I prefer to have, most people prefer to factorise with positive x squared. So you can factorise it like it's as it stands, but a lot of people prefer to do it with positive x squareds. And then we're going to try and factorise this to solve this. You could use a quadratic formula, you could use completing the square as well, but we're going to factorise this because it's quite straightforward. X and x, x times x. 2 times 1, but we want minus 3 when we add them together. So it's minus 1 times minus 2 will give me plus 2, and we'll add to give me minus 3. Now, we have one number times another number equals 0. One of these numbers must equal 0. So either that or this must equal 0. So x equals 2 or x equals 1. So these are the two roots. This is all we had to do to solve this question. But let's just think about what that means on our graph. So it means we're going to cross at 1 and 2. Now, before I draw the graph, I'm going to have a look at this. Wait a minute. I've got a minus x squared. If I've got a positive coefficient of x squared, then I get a U-shaped graph. Okay, and if I get a minus x squared, then I get an N-shaped graph. You might think of that as a smiley face for positive. An unhappy face for negative might help you remember. So we're negative, so we're going to have an unhappy face. We're going to have an N-shaped graph like so, and it's going to cross at 1 and 2. And another interesting point that you're often asked to find is this point where it crosses the y-axis. Now that, okay, is where the x value is equal to 0. So put 0 into this, you get 0, you get 0, you get minus 6 is where it crosses the y-axis. Right, next question. Should be a bit more straightforward. 30 seconds, see if you can do this one. Right, now this one, we've got the graph drawn here. So here's the x-axis here, okay, and we're looking for, remember, the roots is where it crosses the x-axis. Now we can either do it by the graph or we can do it by the factorising. We can see that if you do it from the equation, we can see x minus 1 must equal 0, or x plus 2 will equal 0 in this case, because it's already factorised, so x equals 1 or minus 2. And here we've got on the graph where it crosses is at 1 and where it crosses is at minus 2. So again, x equals 1 or minus 2. So going on to the next question. See if you can find the y-intercept. This should only take 30 seconds too. Okay, so find the y-intercept. Remember what I said about the y-intercept? The y-intercept is going to be where the x value is 0. So put 0 into this, okay, and we get f of x is equal to minus 1 times by minus 3 times by minus 2. So that gives me 6. That gives me minus 1 times 6 is minus 6. So it's going to cross at minus 6. With that minus 1 in front, that means we get minus x squared coming out. So we have an n-shaped graph. And we know that it will cross at 3 and 2. So if you actually wanted to finish this off, okay, that point's going to be, 2. That point's going to be 3. And this point is going to be minus 6. Okay, I'm going to find the turning point of this quadratic function. I'm going to give you 1 minute to have a go at this one. Right, there's two ways to do this question. If you're doing IGCSE, then you could just differentiate it to find the turning point. So if you find f dashed of x, you should know how to do this if you're doing IGCSE. Differentiate this, you get 2x. Differentiate this, we get minus 4. And the turning point is where the differential, the gradient function, equals 0. So 2x minus 4 must equal 0. So that means 2x equals 4 or x equals 2. So we know that the turning point is x equals 2. We can put that back into this. So we get 2 squared minus 4 times 2. So that's 4 minus 8 plus 4 is 0. So you get a y value equal to 0. So the turning point will be at 2, 0. Now another way we can find the turning point, if you can't differentiate and you've forgotten how to do that, is to complete the square. So if we've got f of x equals, if we complete the square, we halve this value to get minus 2, square it. And then a quick way to, if you can't, rather than just multiplying it all out, if you always take away that value squared, so that's minus 4, and then add that number on there onto the end, you get the completed square format. And in fact, it's a perfect square. And what if you know your transformations, this will tell you that it's been translated right by a value of 2. So if you have an x squared graph is normally like this, so the minimum point is always at 0, 0, and you need to know what your x squared graph looks like. So make sure you know that it's there and the minimum value is at 0, 0. We shift it to the left 2, we get this point here. And I'm going to be doing more about transformations of graphs later on in this video. So you can see that the minimum point is given by this is also 2, 0. If we had a number on the end that we add or take away, that shifts it up or down and will give you your y coordinate. Right, finish off this section on quadratics. Which of these graphs represent this quadratic function? So if you're listening to what I said, this should just take 30 seconds to do this. Right, there's your 30 seconds. So basically what this means is that we're going to shift to the right by 3 because we've got a minus 3 in the brackets. Okay, and this means we're going to shift up by 3. So therefore, if we've got an x squared graph, it will be shifted to the right 3 and up by 3. And which of these? Well, that's gone down, that's gone left, this one's gone right and up, so it must be this one. That is the graph that represents x minus 3 squared plus 3. Another trick you could put in is just to put some values in. You might put x equals 0 in and see if it corresponds, although it doesn't show you where it crosses at, so it might be a bit tricky. Right, moving on, we're going to look at some transformations of graphs. And I've put on the OneNote, if you actually click on these, you can see the actual applet I'm going to use. But I'm going to call upon the actual full version by getting the link. So we can just have a little bit of look at some transformations. Okay, now transformations of graphs. This is a graph of f of x equals sine x here. And what I've done is I'm showing you, I'm going to demonstrate what happens if you add a to inside the brackets. So if we add a, so if we add 10, 25, 35, 45, we can see it's shifted the graph left. Okay, the graph was originally this red one and it's been shifted to this blue one and it's shifted left by 45, and you can see it more easily if I make that 90. So we can see, look, the original graph was at 180, it's now crossing at 90, its peak was at 90, it's now got a peak at 0, so that shifts it left. Now if we make the a negative, then it shifts it to the right. Okay, so that's what that one does. And then when we look at this graph, what happens if I change the value of b? Well, it's 0 at the moment. If I make it bigger, I move the graph up by b. So if I make b 2, you can see where it crossed the y-axis is moved up to 2. And if I make it negative, it will shift it down by that amount. So you can see what that does. So those are all translations. So if you want a proper name for this, this one's a translation with vector a0. Okay, and this one's a translation with vector 0. Sorry, that's not a0, so it's going to be minus a0, and that's going to be 0b. And if we look at the stretches, okay, so if I have f of c times x, so if I times the x value by a value, look what happens to the graph. Oops, I need to just make sure it's visible. There we go. Let's go back to 1. So it's times by 1 doesn't change anything. But if I times it, you notice it bunches it up. Okay, so we've got a stretch here. Now because it's bunching it up, so it's moved that point from there to there, we call it a stretch scale factor a half for c equals 2. And if you make it 3, then it bunches up by a factor of 3. It's now at 60. So it's stretch scale factor 1/3. Okay, and all these stretches are parallel to the x-axis, how we describe them. Okay, so I'm just going to, you can just see that moving, and I'm going to hide it now. Now look what happens if we times on the outside. So we times by 1, nothing happens to the graph. But as soon as we times by 2, we can see the graph gets twice as tall here, but doesn't move where it crosses the x-axis. Again, it's another stretch, and this stretch is parallel to the y-axis, and the scale factor is exactly the value of the number you times by. and then we look at some reflections. So look at this reflection. This one actually reflects in the y-axis. Now, unfortunately, I've chosen a bad graph here, sine x. This one looks like it actually go back. This one reflects in the x-axis, and this one actually reflects in the y-axis. I'll show you the cos curve, which I did here. Okay, it'll be easier to see. So here's the cos curve. If we do the reflections, you can see that one reflecting in the x-axis, and this one. So if I just do this one, it doesn't seem to move because it's reflected in the y-axis, and it's symmetrical about the y-axis for the cos curve. So now, rule of thumb, if what's happening to your function is inside the brackets, then all the movement's in the x direction, and generally the opposite of what you think. Remember, the stretches made it smaller by the scale factor. The translations, if it was a positive value, it went to the left, and if it was a negative value, it went to the right. So they all happen inside the function. Okay. Now, if you're going to be outside the function, like this minus sign, or this stretch d here, or this one adding on b, then all the movement's in the y direction, and it happens to be exactly what you think. Now let's put those into some questions. So here's a question. Just going to get that scaled up a bit better. There we go. Right, let's give you just 30 seconds to try and do that using what we just said. Right, so what you can see is we have a reflection in the y-axis and the x-axis here. So that one is going to be this one, f of minus x. Going to the next one. Another 30 seconds to try and work out what's going on here. Okay, so what we've got here is we've got y equals x cubed. Now the x cubed graph, you need to know, goes through the origin like this. So if we were to draw the x cubed graph, it will look like that. And you can see this has been moved down by 3, so therefore it's f of x minus 3. Right, another 30 seconds to have a look at this one. Okay, so what we've got here, if you've got the x cubed plus 3 graph, now the x cubed graph we know goes through like here, and if we shift it up 3, that will give me the x cubed plus 3 graph. Now this graph is not the same, it's been reflected in the y-axis. So when we reflect in the y-axis, that means the movement's left and right. So it's going to be f of minus x. I'm just going to check my previous reflection. I've made a mistake here. Sorry about that. This one was wrong. Okay, it's reflection in the x-axis, and therefore, because the movement's in the y, it's always on the outside of the function, and we get minus f of x. Sorry about that. Let's go back down to this one. So this one's a reflection in the y-axis, so it's f of minus x. Going down to the next question. 30 seconds. Okay, so we've got f of x equals 1 over x. Now this graph looks like this, if we draw it. So the 1 over x graph looks like that. Ignore this line in the middle, it shouldn't be joined up like that. So if it has an asymptote there, an asymptote there where it never crosses on the y-axis and on the x-axis. Now what we can see is the asymptote here, the line it doesn't cross, has been moved up by 4. So the graph must have been moved up by 4. So therefore this is f of x plus 4. It went up in the y direction, so the plus 4 is on the outside of the function, not the inside of the function. Okay, another one. Okay, so let's have a look at this one. And we've got 1 over x again. Remember what the 1 over x graph has an asymptote where the y-axis is. And what we see is the asymptote was here and it's now been shifted left 2. Now remember, when you shift to the left 2, that's going to be inside the function, the opposite to what you think. So it's actually going to be f of x plus 2 in this case. Okay, next one. Right, this one's a bit more tricky because you haven't got a standard 1 over x graph. Okay, they've got a 1 over x plus 2 graph. Now what that does is shifts the 1 over x graph this way too. So you immediately got an asymptote here. So our 1 over x graph has been shifted that way, which you can see here. There's the asymptote there. But what has happened to our graph has also been shifted up by 2. Okay, so from here, which is this graph, we have been shifted up 2. So if you add 2 onto every value, you get f of x plus 2. Okay, another 30 seconds. I think there's just a couple more of these, and then we'll be on to the bigger problems. 30. Sorry, I didn't. The mic was off then. Let me just go over the explanation there. It looks, and you might think there's a reflection going on in the y direction, but the problem is the reflection's in the line y equals 2, so it can't be that, and we don't have a transformation for that. It's a reflection in the y-axis here, which gives us f of minus x. Right, let's move on to the next question. 30 seconds. So we've got the main function shown in grey, so this function, and what you can see is the graph has gone up by an amount of 3. So shifted up by a value of 3. Actually, I'm not sure it has shifted. Wait, this is shifted down. Yeah, it's all shifted up. Just checking that. Shifted up by 3, shifted up by 3. It's just hard to see it on these values. It has shifted up by 3. So we're adding on 3 after we've done the function. So we get f of x plus 3. Next one. I think this is the last of these. Okay, so f of x is shown in grey, and we can see it's definitely a reflection in the x-axis. So therefore it's a movement in the y direction, so the thing happens outside the function, so it's minus f of x. Right, here we go. We've got a little bit of a problem to solve. I'm just going to make that a bit smaller. There we go, so you can see the whole problem. I'm going to give you 3 minutes to think about this problem. I'll give you a clue. It's an exponential decay problem. So it's got to do with exponentials. So I'm going to give you 3 minutes to have a go at this. Right, okay, so we've got a half-life problem going on here. So, radioactive element, its half-life is 5,730 years. This means that half will decay into another element. Suppose you start with 100 grams, so we'll start with 100 grams. Now, we want to know the time it gets to half of that. Well, it's given by 5730. So, we could plot 0 at 100. And when we can plot 50 at 5,000 and a bit, getting on for nearly 6, so round about here. And then what we can realise is the next time it'll be half, 25 will be at double that. So if you do, if you just times this by 2, so what we're going to get? We're going to get 10,000, it's 11,460, aren't we? We're going to get about 11,460, so it's going to be around just about between 11 and halfway between 12. It's going to be at about 25, so it's going to be a point there. And then another 5,700 down, so that's going to be 11,4 something, so it's going to be about 12, 17. It's going to be about 17, it's going to be around about the 12.5. So we can see our graph doing this. Okay, not a very accurate graph. Estimate when the mass of carbon-14 will drop to 21 values, so we just do that and we can use our graph. This isn't going to be very exact. By the way, I've drawn it. You will obviously in an exam have a much more accurate graph to draw it on and get a better answer than this. But that's essentially how you go about doing this question. Right, I've got a nasty little parabola question. Just going to zoom out a little bit here so you can see it all. See if you can work this one out. Again, I'll give you 3 minutes to think about it. Right, here we go. So we want to write this in completed square form up here. Okay, so what we do is we halve this value, so you get x plus 10 all squared. Now if you remember, what I suggest you do is, if you're going to do this in completed square form, we write x squared plus 20x plus 89. So that's going to equal x plus 10 squared, subtract the 10 squared, and add on the 89. And that's minus 100 plus 89, so that's going to give me minus 11. And what we can see is, that corresponds to the coordinates here of minus 10, minus 11 for that vertex there. Now we want to find the coordinates of the vertex when it's an x equals 17. So we're going to shift along the y equals x minus 1 graph. So therefore, if y equals x minus 1, okay, remember here we've got x was minus 10 and y came out to be minus 11 there. Then it stands to reason if x is 17, then y is going to be 17 minus 1, which is 16 for that vertex. And therefore, if we've got that as the equation of our vertex, we know that these two values give us our vertex. Okay, so therefore, the f of x will be x minus 17 squared. Because we shifted 17 that way, then it was a minus. When it was a plus 10, notice we shifted that way. Okay, and then all we need to do is add on the amount we go up or down. And it's gone up by 16 because the y value is 16. So that is another way of doing our equation of a parabola in terms of completed square form. And it just says find the equation. So we don't need to use this equation and do it in this form. We can just write it out in this form, and that makes a perfectly good answer. And it's much easier to do once you've done that. Right, okay, that's all on the non-linear graphs for level 6 or 7. Tomorrow we're doing levels 8, 9 non-linear graphs. And be good if you can come and join me and learn a bit about that then too. Goodbye.